problem was there was a solid shaft. One end of the shaft was supported to C, and another end was free, and the shaft is subjected to different torsional loadings. One concentrated torsion at the free end, another concentrated torsion 0.2 meter away from the support, and at the middle part 0.2 meter length, the shaft was subjected to uniformly distributed torsion. And then we have to determine the diameter, and the allowable shear stress of the material is 60 MPa. Allowable shear stress of the material, that means shear strength of the material is 60 MPa. Then we have to determine the size of the shaft or the diameter of the shaft. So as the shaft is subjected to different torsional loads, so we have to determine the maximum torsion developed in the shaft, maximum resisting torsion developed in the torque. So we can do it similar to bending moment diagram or shear force diagram. Have you learned about the bending moment diagram already? Hello? Could anyone tell me, have you learned about the bending moment diagram and shear force diagram already?
No, sir.
Oh, I see. So it will be a little bit difficult. So bending moment diagram means it is a diagram that shows the variation of bending moment along the length of the structure. Or the shear force diagram, that means it is a diagram of shear force that shows the variation of shear force along the length of the structure. That means how much shear force is developed at a location along the length of the structure if for the load subjected to the structure. So that is the shear force or bending moment diagram. So I will explain it here. So we will first show the variation of shear torque or torsional force along the length of the shaft. So this is the shaft, and this shaft is subjected to a concentrated torsional force, another concentrated torsional force, and this part is the uniformly distributed torsional force. So we will show the variation of developed torsional stress in the shaft along the length of the shaft. Okay, developed torsional stress in the shaft along the length of the shaft. So this is the length, and there are two axes, x and y. This x-axis represents the length of the shaft, and y-axis represents the torsional force developed in the shaft. And the upward is positive, downward is negative. So if we start from here at the free end is subjected to a concentrated or constant torsional force 800 Newton meter. And if we apply the right hand thumb rule, so this torque is positive, right? Because if the thumb goes away from the surface, then the curling direction is similar to the direction of torque. So this torque will be positive. So this is this torque is 800. So say it is 800. Okay, and if you go from this point to that point, there is no additional torque. There is no additional torque. So if you take a section from here, if you take a section at anywhere between this length, then the developed torsion will be similar to this one. Developed torsion will be similar to this one. That means at anywhere in the length of the between these 2 points, the developed torsion will be similar to 800. So up to this, if it is 0, then this point will be 0.5 meter length. So up to this length, the developed torsion will be 800. So it is 800, constant 800. And then come to this point. So if we apply the right hand rule, so the curling direction of the finger will be anti-clockwise, but the applied torsion is clockwise. So this torsion will be negative torsion. Okay, this torsion will be negative torsion, and these torsions are uniformly. This torsion is uniformly distributed. So if we start from here and reach to B, if we start from here and reach to B, the total torsion will be 4 times 0.5. Okay, it is the uniformly distributed. That means in 1 meter length, the applied torsion is applied torque is 4 kilonewton meter. Applied torque is 4 kilonewton meter in 1 meter length. So the total length is 0.5 meter. So the total applied torque will be 4 times 0.5. That means 2 kilonewton meter. 2 kilonewton meter, and this unit of this torque is Newton meter. So we have to convert this 2 kilonewton meter into Newton meter. Then it will be 2000 Newton meter torque, and that torque is negative because the direction of the torque is clockwise direction. So that torque will be negative. So if you start from here and reach to here, then this torque will be negative. So ultimately, at this point, if you reach here, at this point the resultant torque will be minus. Total negative torque is 2000 and positive torque is 800. So the resultant torque will be 1200 Newton meter, and that will be a negative. So at this point, the resultant torque is 1200 negative. And if you learn how to draw the shear force diagram, then you will see the diagram between this length, within this length, the diagram within this length will be straight, inclined straight line. Because at this point the total torsion is 800, and at this point the resultant torsion is 1200. So the variation of developed torsion from this point to that point will be indicated by a line joining this point and that point. You will learn it clearly when you learn how to draw the shear force diagram and bending moment diagram. Do not worry, it will be very clear from there. Okay, and then come to here. So in this zone, that means from point B to this point, there is no additional applied torque. So at anywhere in this length, the resultant torque will be similar to 1200 because there is no additional applied torque. So the total torque within this zone will be constant, and that will be negative 1200 Newton meter. So it will go straight. This line indicates that at anywhere the torque is constant, right? That is similar to 1200 at anywhere in this zone. That's why it is horizontal. But in this zone, it indicates that the resultant torque is varying, and the resultant torque varies from 800 to 1200 linearly. And at this area, the resultant torque is 0. Okay, and then come to here, and when you will reach this point, there is another 400 Newton meter torsional force, and that is anti-clockwise. So it will be again positive. It will be positive. So at this point, actually you will get 2 points. Another point is just left to this, point, and just right to this point. And if you reach, if you are just left to this point, and then you will not consider this torsional force. You will not consider, because if you just left to this point, you will not face this torsion. And if you cross this point, that means if you just cross this point, then you will face this torsion. So in that case, that means just left to this point, right to this point, the resultant torsion will be 1200 plus 800, 400, because this 1200 is negative torque and this torque is positive torque. So the resultant torque at this point will be minus negative 800 torque. And if you goes from this point to the support, there is no additional applied torque. So at this zone, the developed torque will be constant. That will be similar to 800. So that's why it is it is a straight line, and it is a subject. It is a support. So this support will carry this 800 torque. So at this point, total torque or the resultant torque will be 0 at the support. So this is the torsional diagram showing the variation of developed torque along the length. Okay, so go to the problem. Basically, we have to determine the size of the shaft, and the allowable shear stress of the material is 60 MPa. That means at anywhere in the shaft, the shear stress will not exceed this value. If the shear stress at anywhere in the shaft exceeds this limiting value, then the shaft will fail. Okay, shaft will fail. So we have to determine the location. We have to determine the location where the shear stress will be maximum. Where the shear stress will be maximum, and we know the equation of shear stress is due to torque is T rho Z, and the maximum equation of maximum shear stress is T C Z. For solid shaft, C will be the radius of the shaft, and Z is constant. So again, the maximum shear stress depends on the maximum value of torsion, maximum value of torsional force. So along the length of the shaft, the maximum torsion is here. Maximum torsion is here. So the maximum stress will be developed at this location. Maximum stress will be developed at this location or in this zone. In this zone, the maximum shear stress will be same. To determine the size of the shaft, we will consider the maximum condition or critical condition. So the maximum stress is tau max CZ. T max. That means the maximum developed torque, and C actually it will be small c. C is the radius of the shaft, and Z is the sectional properties of the shaft, and we know the maximum allowable maximum allowable shear stress will be 60 MPa. To convert it into Newton meter square, that is this 60 will be multiplied by 10 to the power 6, and maximum torsion is 1200. And if we have to determine the diameter, so the radius will be d by 2, and it is the equation of sectional properties, that means polar moment of inertia. So in this equation only unknown is d. So from here the value of diameter will be 0.046 meter, and to convert into millimeter it will be 46.7 millimeter. That is the diameter, that is the required diameter of the shaft. Okay, and any question in this problem? Because as you have not learned about the shear force and bending moment diagram, this problem will be little bit complicated. But when you learn that topics, that means the shear force diagram and bending moment diagram, then it will be very much clear to you. So, do you have any question in this problem? Okay, I can proceed to next topic. Angle of twist. Angle of twist or angle of rotation, we have already learned what is the angle of twist. Angle of twist means it is a subject, it is a shaft, and this shaft is subjected to a torsional force, two torsional force, T1, T2, and angle due to torsional force, this shaft will be twisted. Okay, this shaft will be twisted, and if we take a segment, a small segment, anywhere in the shaft, and if we draw it in the larger scale, then this figure shows the section of this small element, this small element in the larger scale. And if we look at here, actually due to this torsional force, this circle or this section will be rotated. Actually, due to the torsional force, the section will be rotated, but the circle will remain circle. Circle will remain circle, but the section will be rotated. So this surface will be rotated, and the surface behind this front surface, that means the back surface, will be rotated also. But the rotation of the front surface, and rotation of the back surface will not be same, and that the rotation, the difference between the rotation is known as the angle of twist. Okay, angle of twist. Say this surface has been rotated by 2 degree or 2 radian, and the back surface has been rotated by 1 radian. Then the angle of twist will be 2 minus 1, that means 1 radian. That is the angle of twist. And we have to derive an expression to determine the angle of twist. So, this shaft has variable cross section along the length. So, different values of torsional force. So, at any location, the resultant torsion, internal resultant torque is Tx. Tx means it is the resultant internal resultant torque or developed torque. It is a function of x, Tx, and Z is the polar moment of inertia, as the section is varying from the support to end. So again, the polar moment of inertia will not be constant along the length. So it will also depends on the value of it will also depend on the location of the section from the support. So we can define it as Zx. Zx means the polar moment of inertia as a function of x at a position x from the support, and angle of phi is the angle of twist of one end with respect to other end. That means it is the total angle of twist from the with respect to the support of the free end. And according to hook law, at the very beginning, I have told you that the all torsional formula will be applicable for elastic material. Elastic material, that means stress and strain will be proportional to each other, and Hooke's law will be applied to for linear material, for elastic material. And according to Hooke's law, you know, gamma is the shear strain. Shear strain equals to shear stress, and G is the shear rigidity or shear rigidity. So, and again we know shear stress due to, as the T is a function of x and J is the x rho Jx. And if you substitute this expression in this equation, then the equation of shear stress will be this. And if we is equal
স্যার কথা আটকে আটকে আসছে স্যার।
5, and to get it we have to integrate this equation from okay এখন শুনছেন
স্যার? স্যার বোঝা যাচ্ছে না স্যার।
হ্যালো
স্যার বোঝা যাচ্ছে না
স্যার, নেটওয়ার্কে
স্যার কথা আটকে আটকে আসছে স্যার।
নেট প্রবলেম। এখন শুনুন
না স্যার,
একটু ওয়েট করো, ওয়েট প্লিজ। ওকে, যারা আমি তাহলে ইয়ে কানেকশন করি, মোবাইল কানেকশন করি। Completed up to this point, and did you hear it? The angle of phi, angle of twist phi, it was Tx dx Tj z. Tx is the developed torque as a function of x, and z is the polar moment of inertia as a function of x. And if we integrate from 0 to L, that means over the total length, then we will get the total angle of twist from of one end with respect to the other end. And if the applied torques are constant and the cross section also is constant, then the equation of angle of twist will be TLJZ. T is the constant applied torque, and L is the length of the shaft, and Z is the polar moment of inertia. And if the shaft is subjected to
স্লাইড
স্লাইড তো দেখা যায় না।
দেখা যাচ্ছে না, ওয়েট। এখন দেখছো?
জি স্যার দেখা যায়।
জি স্যার দেখা যাবে।
থ্যাংক ইউ। So আমি বলছিলাম যে the angle of the phi is the total angle of twist of one end with respect to the other end, and as the cross-sectional area of the shaft is varying from one end to another end, so we have to integrate the polar moment of inertia from one end to another end to get the resultant polar moment of inertia. And again, as the torque is varying from one end to another end, so again we have to integrate the developed torsion from one end to another end to get the resultant torsion. So the total angle of twist of one end with respect to another end will be determined from this equation. So this equation it is a general expression, and for any specific problem, that means if the cross-sectional area of the shaft is constant and the shaft is subjected to a constant torsion, one torsion, then the equation of angle of twist will be TLJZ. It is simplified, or it is a equation of angle of twist for any specific problem. And if the shaft is subjected to different amount of torque at different locations, and if the cross section of the shaft varies from point to point, then the angle of twist from one end with respect to other end will be TLJZ. That means we will determine the angle of twist for each segment, and if we sum it, then we will get the total angle of twist of one end with respect to other end, and it will be clear if we solve a problem. This is another problem. Actually, there are three gears. One gear is A, another one is C, another one is D, and these three gears are attached to a shaft. It is a solid shaft, and shaft is A to E. E is the fixed support, and E is the fixed support, and there is another support B. And at B it is frictionless support. Frictionless support, that means if you want to rotate this gear, or if you rotate this shaft, no shear stress or no frictional stress will be developed at support B. Okay, it is a frictionless support, and the shear modulus of elasticity of the material of the shaft is 80 GPa. That means gigapascal, and the shaft has a diameter of 14 millimeter. Okay, it is a solid shaft, and its diameter is 14 millimeter, and there is a point on gear A. The point is P. There is a point at the outer surface on gear A. Determine the displacement of the tooth P. Basically, those are known as tooth of the gear. So we the name of this tooth is P. Then we have to determine the displacement of the tooth P, and if this gear, that gears are subjected to this amount of torsional force, and the shaft turns freely within the bearing at B, and already I have told it that the support is frictionless. Okay, so we have to determine the displacement of the tooth P on gear A. In the previous two equations, this equation is applicable if the shaft has constant cross-sectional area and it is subjected to one torsional force. Okay, and this one is applicable for if the shaft has constant, shaft has different cross-sectional area, but concentrated torsional force. Concentrated torsional force, not the variable torsional force, concentrated torsional force. So from this figure, it is seen that this shaft is subjected to different torsional force at different locations. So you have to use this equation. We have to use this equation. To use this equation, we have to determine the developed resistant torsion within length L, and we have to determine the polar moment of inertia of the section within the length. So as the shaft diameter is constant over the length, so this J will be constant along the length, but all lengths are not subjected to constant torsional force. So we have to determine the developed torsional force within different length. Okay, so first of all, we will determine how much torsional force is developed within this length, and within this length. Okay, so if you want to say if you cut from here, cut anywhere within A and C, and if you draw the free body diagram, then it will be similar to this one. So applied torque is 150 Newton meter, and developed torque is TAC. That means the developed torque within length AC. And if we apply the equilibrium condition, that means the applied torque will be equal to developed torque. So as the applied torque is 150, so the developed torque will be also 150. And if we take another section from here between C to D, and if we draw the free body diagram of any side, left side or right side, and if we draw the free body diagram of right side, then it will be similar to this. The applied torque 150 applied torque anti-clockwise, and 280 applied torque clockwise, and say the developed torque within length CD is designated by TCD, and if we apply again the equilibrium condition, then the developed torque within length CD will be minus 130, because this one is positive according to thumb rule. This one is positive, that one is negative. So the resultant torque will be 280 minus 150, that means 130, and that will be negative. That's why it is negative 130. And again, if we want to determine the developed torsional force within this length, so we have to take a section from here. So that section is this one. This one is the applied torque, and the developed torque within this length D is TDE. And if we apply again equilibrium condition, so positive 150, negative 280, negative 40. So the resultant internal torque will be negative 170 Newton meter. And the sectional properties will be constant, because the diameter of the shaft along the length is constant, and the radius is diameter is 14 millimeter. Right? Diameter is 14 millimeter, so C will be 0.7 millimeter to convert into meter, 0.007. So that is the sectional properties. And then we will apply this equation TLJZ. Summation about TLJZ as different segment is subjected to different amount of internal torque. So we have to apply this equation. So from A to C, the the developed torque is 150, so that is positive 150, and L is the length is 0.4. Here the from A to C length is 0.4, C to D 0.3, and D to E 0.5. So this is the length, this is the J, and Z is also constant along the length, that is 80 GPa. To convert into Newton meter, it will be multiplied by 10 to the power 9. And from C to D, the developed torque is negative 130, length is 0.3, and from D to E, developed torque is minus 170, length is 0.5, and this is the J and J. So after calculation, there is the total rotation of gear A is 0.21 radian. That is the angle of twist of gear A with respect to the support. Okay, that is the angle of rotation or angle of twist of this gear with respect to this support, and this angle is constant at anywhere in this section. This angle is constant. That means that angle is also for here, for anywhere the angle is constant. So basically we have to determine the displacement of tooth P. Okay, we have to determine the displacement of tooth P. So this gear will be rotated by amount of 0.21 radian. So this point will be also shifted, or this tooth will be displaced, and the displacement, if we want to determine the displacement, so the total displacement will be rho theta. Okay, the displacement is rho theta. This one is the angular displacement, and rho is the distance from the origin to the point. So the total angular displacement of that point will be this one. 100 is the radius of the gear. I think, yeah. The radius of the gear is 100 millimeter. It is given. So the total angular displacement is this one. And then you have to determine in which direction the tooth P will be rotated. In which direction? So from this result, it is observed that the value is negative. The value is negative. That means the resultant torque this gear will not be rotated along this line. It will be rotated clockwise direction. As it is negative, because we have according to thumb rule, if we know this direction is positive, this direction, anti-clockwise direction is positive, but this rotation indicates the negative value. That means this value, this gear will be rotated clockwise direction. Okay, and there is another problem. There is the 2-inch diameter solid cast iron shaft. It is a solid shaft. It is made of cast iron, and diameter of the shaft is 2 inches, and this shaft is inserted to the soil by 24 inches. This shaft has been inserted to the soil by 24 inches by applying a torque at the top of the shaft using a torque wrench. It is a torque wrench, and the applied force is 25 pound, and the arm and lever arm or the distance between these two forces is 6 plus 6 12 inches. 6 plus 6 12 inches, and the length of the shaft above the soil is 36 inches. Okay, 36 inches, and it is assumed that it is actually idealized. In practical case, we from the previous problem we have seen that if we apply torque to this type of shaft, what is the time? Okay. It's time over. So better we will explain it in the next class. Okay, we will explain it in the next class because time is over. We will need at least 10 minutes to explain it. Okay, and do you have any question? Hello?
স্যার
Yes, sir.
অ্যাঙ্গেল অফ টুইস্টের যে ফ্রন্ট সাইজ আর ব্যাক সাইডের যে বিষয়টা ওটা স্যার একটু বুঝি নাই।
Okay. Actually, if we apply torque, each cross section at each location along the length will be twisted, right?
Yes, sir.
Say if you take a cross section here, if you take another cross section, each cross section will be rotated. But from the previous class, we have seen that the rotation is varying from support to free end. That means at support the rotation is 0, and if you go far away from the support, the rotation will be greater, right? Rotation will be greater. So due to this applied, imagine this shaft is subjected to only this torque, only one torque, and due to this torque, each section along the length will be rotated, and the rotation of different section will not be same. It will be greater if you go far away from the support, and it will be smaller if you go closer to the support. That means the angle of rotations are not same at different points. So we have taken element here, right? We have taken element here, and the length of this element is dx. So this element will have two cross section. Another is here, another one is back, right? One cross section is at the front, another cross section is at the back. So the front section is little bit far away from the support, and the back section is little bit closer to the support. So angle of twist of this section or angle of rotation of this section will be greater than the angle of rotation of the back section, right? Angle of rotation of the back section. So the difference of the angle of rotation of the front section and the back section will be the angle of rotation of front section minus angle of rotation of the back section. That is the angle of twist. Understand? That is the angle of twist.
Yes, sir. বুঝছি স্যার।
And that is designated by delta phi. So basically, what is the difference between angle of twist and angle of rotation? Angle of rotation means the angle of rotation means or angle of twist means the angle of rotation of one surface with respect to other surface. Angle of rotation of one surface with respect to other surface, because say if we assume this surface due to this applied torque, this surface has been rotated by say 10 radian, and the back surface has been rotated by say 6 radian. Okay. So the angle of rotation of the front surface is 10 radian, angle of rotation of the back surface is 6 radian. So the angle of rotation of the front surface with respect to the back surface will be 6 radian. Okay, we have to determine the angle of relative angle of rotation, not the total angle of rotation. The relative angle of rotation. Relative means to determine the relative rotation, we have to assume one point fixed, another point movable. Say if one bus goes with 60 km/h and another bus goes with 40 km, and if we want to determine the relative velocity, then we have to assume that one bus is fixed, another bus is moving. Similarly, if we want to determine the relative rotation, then we have to assume the one surface is fixed, another surface is movable or rotable. So the relative rotation will be the total rotation of the front surface minus the total rotation of the back surface. That means we are assuming that back surface is fixed. Okay, any other question?
No, sir.
Okay, thank you very much. Okay, that's all. You can leave now.
Sir, assalamu alaikum.
Assalamu alaikum, sir.
Wa alaikum salam.
Assalamu alaikum.
Salam. Have a good day.
Assalamu alaikum, sir.